On slide 90, we start with the distal outcome modeling. And the first step is to remind ourselves of how we do distal outcome modeling in a latent class analysis as opposed to in a latent transition analysis. This was discussed on slides 17 to 20 in the early parts of the Webtalk. Slide 91, then we have odds and odds ratios for two predictors. For an equation, log odds for u, a binary variable, as a function of two x variables, a plus b1 times x1, b2 times x2, where the log odds is same as a logit. That is, we do logit regression. Odds ratio interpretation is that the e to the power of b1 is the effect of x1 irrespective of the value of x2 as a benefit of logistic regression modeling. And the odds ratio for the effect of x2 is e to the power of b2. Now the latent class model is one where you have one single latent class variable c, and you have the distal outcome u here, and you have a predictor x. So x influences c and u, and the influence of x on u is the same for all classes c. That is, there's no broken arrow indicating an interaction model, but it's a main effect model here. A logit regression then with x and a latent class predictor c is like this. That is, it is the intercept that varies across the latent classes c, and that's the same as the negative of the threshold, which we call t here. And then we say that the odds ratio effect of x is e to the power of b, that is e to the power of this effect here, irrespective of which latent class we are in, by the rules that we established up here. And the odds ratio effect of the latent class, that is the effect going this way, is expressed in terms of the u odds, that is the odds of getting it right versus getting it wrong, for a certain class, divided by the odds for the last class. And it's not influenced by the value of x at all. Now, slide 92, you have an interaction here between x and c, so that the effect of x varies, effect of x on u varies across the c classes. The logit regression then is has a slope that also varies across the classes. And written out in terms of thresholds, it looks like this. Just as a reminder. So turning to slide 93 then, we're going to get back into the reading example and take a look at a distal outcome predicted by an LTA. So we have the three classes again here and the 5 items. And we remind ourselves of the pattern of probabilities. And we're going to focus on the site item, which is a clear indicator of being in class 3. That is, the probability of getting that item right is very low in class 1 and class 2, but very high in class 3. So that's a good item to discriminate among classes 3 versus the other 2. And that's what we're saying in this bullet here. So one question one could have then, what can we say about the likelihood of mastering the site item at spring first grade, the last 4th time point, based on development from kindergarten fall to kindergarten spring? That is, by the end of kindergarten, what can we say about the likelihood of mastering site 1 year later? Here's the model diagram that we can draw. We have then 2 time points, fall kindergarten, spring kindergarten. We have the poverty covariate, which influences the class probability at the starting point and at the ending point. That is, it influences the transitions. It's a main effect model because we don't have C1 influencing poverty's influence on C2. So the transition follows the main effect model. You could have the interaction effect model too, but for simplicity we choose this model, and it's also a better fitting model. Now the distal outcome site 4 at the 4th time point is influenced by poverty and by C1 and by C2 and an interaction of C1 and C2 as indicated by this broken arrow. So it's in effect influenced by the transition paths. Here on slide 95 then we can get back to looking at different transition paths. Here we have 3 rows corresponding to 3 transition paths. So we're talking about fall kindergarten, spring kindergarten, and the individuals can be in class 1 fall and stay in class 1 spring, or go to class 2, or start in class 2 and stay in class 2. Other combinations are so much less frequent that we can ignore them here. So those transitions have 21, 44 and 20% respectively in this sample. So then we can ask ourselves, well, for those 3 transitions between the latent classes, what's the probability of getting the site item right in the spring or first grade? If we look at those in the poverty group, we see that the probability of getting the item right is lowest when you stay in class 1 in kindergarten, considerably higher when you move up to class 2 by the end of kindergarten, and highest if you start in class 2 already in the fall of kindergarten. So you have a clear distinction here in the probabilities. Now with poverty equals 0, you have a much higher probability of getting that sight word item right in all 3 of the transition paths. So that's higher than that, this is higher than that, that's higher than that. To do this kind of modeling then is an exercise in using this dot approach, which refers to a combination of latent classes. I'm going to show you the Mplus script for that in detail. Now once you've done this analysis, you want to do a check to confirm that the latent classes stay the same even after adding the site 4 item, and they do in this case. Now the probabilities for site 4 that I show up here at top right, they can be calculated via thresholds and the slope in the regression of site 4 on poverty. Using the model constraint command as I show in the next slides. It's not available via the calculator that we talked about earlier, because this is the case where the items are influenced, where the site item is influenced by more than one latent class variable, C1 and C2. Here's the Mplus script excerpt. So you have C2 on C1, and C1 and C2 both regressed on poverty, and we have site regressed on poverty as well, and we give it a label which we may use later on. And here's then the essence of the dot command. So inside the overall part of the mixture model, you refer to a combination of classes, C1 dot C2. So you have C1 number 1, C2 number 1, and then you have C11, C22, C11, C23, C12, C21, etc. down to C13, C23. And within each of these combinations, you have the usual threshold labeling. So when you move from C2 class, when you stay in C1 class 1 here, which you do here, here, and here, the first time point thresholds labeled 1 through 5 are held equal, whereas the C2, when the C2 classes vary, which they do, the thresholds for the second time point vary across those C2 classes as we usually have them do. We want the thresholds to vary across these classes, but it's only the thresholds for time point 2. For time point 1 thresholds, we have equality 1 through 5 here. And then similarly throughout the whole script. So that's a dot command, very flexible approach where you can specify equalities in any which way you want. Now regarding the model constraint statements to compute the probabilities, you have for poverty equals 1, the probability is 1 divided by e to the power of the minus loaded as usual. Well actually you should say divided by 1, I have it correctly here, 1 plus 1 to the 1 divided by parenthesis 1 plus the exponent of the logit, negative exponent. The logit is the threshold plus the slope b that we labeled before times poverty. And since the logit should be negative inside here, you have the positive threshold minus the slope b, and b times poverty equals 1 in this case. So here you have the probabilities for the first row in the transition table, for the second row, and for the third row, the first index pointing to poverty equals 1 as opposed to 0. The odds ratios for the effective transitions on site 4 then can be explained this way. So we're interested in the effects of transitions on site 4. We can compute them in line with those slides 19 to 20 generalized to a multiple time point situation, but they're already given in Tech 15, thankfully, because there's a lot of model constraint statements you would have to come up with otherwise. It's given under the heading latent class indicator odds ratios for the latent classes. It's not a output segment that we looked at before. I don't use it very often. I look at the probabilities of the latent class indicators as a function of the latent classes instead, but you could have odds ratios results also for those relationships between the classes and the indicators. Now let's look at the odds ratios for the different transition examples, the 3 that we looked at before. You have 1,1, that is staying in class 1 through kindergarten, 21% were there, versus 1,2, 44% were in that better performing transition. That has odds ratios 0.150, which is significantly less than 1, which makes sense. We have a very much lower odds for staying in, let's see if I say this correctly, much lower odds for staying in the starting class versus moving on. That's what we hope to be the case. That is better, higher probability for moving on. And we see that. Now you may instead want to compare moving on versus staying, but that's not printed in the output. It is, however, obtained as the inverse of this odds ratio and the inverse of the limits, switching their order, and then you get odds ratio 6.67, which is greater than 1. The confidence interval does not include 1. So in words, if you progress from class 1 to class 2 by end of kindergarten, your odds of mastering sight words at the end of first grade is almost 7 times higher than if you're still in class 1 by end of kindergarten. So you may want to read that and think about it. It's a lot to take in. So it's better to move on than to stay, which is what you want to see. Now, what about being in class 2 already from the beginning and staying in class 2, 20% take that path, versus staying in class 1? Well, that is a very high odds ratio of 33. Clearly different from 1. So it's much better to be able to stay, to be in class 2 already, even if you stay there throughout kindergarten, even if you don't move on. Now then you can ask also, what about that transition path that is staying in class 2 through kindergarten versus moving up to class 2? Well, that's odds ratio of 4.9, significant. So that it's better to have started in class 2 than just having ended in class 2. So that's kind of interesting. And it tells you a little bit of the story of transitions. Now, we also have the odds ratio for the effect of poverty on site 4. Up here we talked about the effect of the C1, C2 classes on site 4. So now we're talking about, if you go back 4 slides, we're talking about this effect here. And that's 0.514. So if you're in poverty, you're about half as high odds to get site 4 right. And that's irrespective of class by this model, as given under the heading Logistic Regression Odds Ratio Results. Finally, then, in this part of the talk, we can ask the question, does the fall kindergarten status matter? Or is it only where you end up in kindergarten that's important for how you do on the site item at the end of first grade? So we can take a look at modeling the effects of latent classes on site 4 here. First model is the model we talked about and that we show in the picture. We have a C1, C2 interaction effect on site 4, and it has these number of parameters, log likelihood and big. Then you can contrast that with a simpler model where only C2 influences site 4. So you don't have that arrow or this arrow. And that gives you 31 parameters. It's 6 fewer. And the way you think about this is that in this model you have 9 different thresholds for site 4, 3 times 3. Whereas C2 only, you have only 3 thresholds. So 3 minus 9, or 9 minus 3 rather, is 6. So that's the difference in number of parameters here. And that gives you a considerably worse log likelihood and a worse BIC. And you can actually then, in this case, test model 2 against model 1. Chi-square with 6 degrees of freedom, 56. So you would reject that model in favor of model 1. So it's not only the ending status that's important, it's having to do with what happened before then also. Now here's an interesting model 3. C1 and C2 main effects, so not the interaction, but just the main effects, that is this arrow and this arrow. Then you have 33 parameters, and I'll get back to the number of parameters in a second. That gives you a slightly worse log likelihood value, but only 1, so multiplied by 2 gives 2, with 4 degrees of freedom difference. So testing model 3 against model 1 gives you, with 4 degrees of freedom, chi-square value of 2. So not significant. So we go with model 3. Model 3 is also more parsimonious, fewer parameters than model 1, and it has the best BIC here, 559 instead of 590 something. Now, so this means that we have, in this model, we actually have 5 thresholds. So 9 minus 5 is 4. So that's the number of, the difference in number of parameters. We have 5 parameters, and this is a little tricky because one can see this regression, that is site 4 regressed on C2 and C1. One can see C2 and C1 as each consisting of 2 dummy variables for representing the 3 classes. So site 4 regressed on 2 sets of 2 dummy variables. And that regression has an intercept, and it has a slope for the C1, the 2 C1 dummy variables, so that's 2 more parameters, and 2 slopes for the C2 dummy variables, so that's 4 plus 1, 5 parameters total. If you add interactions then between these dummy variables, 2 times 2 is 4, that's 4 interactions plus the 5, gives you the 9 parameters, that is the 9 thresholds that we have in the transition model. So that's kind of tricky to deal with, but that's how it goes. And we're going to see how you model this in Mplus. But anyway, the conclusion is it matters where you start in the fall of kindergarten, but it's not the transition that matters so much as where you were at C1 and where you were at C2. So thinking about this, so we're saying essentially then that the effect of being in class 1 kindergarten, that kindergarten status effect is the same whether you move to class 1 or if you move to class 2. So the movement doesn't matter, it just matters where you started and where you ended, which is kind of an interesting situation. And in other contexts, in other real data analyses, you might find that it's the movement that also has an effect. And this is, by contrasting these 3 models, you can see how that plays out. And so these 3 models are of interest to study in detail, and we'll do that in the next segment 20.